All right, we've had a couple more people join. I'll get started here so we don't waste anybody's time. So welcome everybody to the monthly Shukla Academy training. This is lesson number 5. I'm Mitch. Morgan is out traveling today, so you're all stuck with just me, unfortunately. Just a reminder, we're hosting these meetings first Wednesday of every month. They're just quick, informal ways for us to get some information out to all you guys that isn't really included in the standard training videos. And then quick recap, you can see all the training videos under the training materials tab on the website, just like where you would see all the other training videos like maxi, screw, blade, that sort of thing. Last month's training, the cup one, should be up on the website for you all to see now. So let us know if you're not able to see it, but last I checked, it was good to go. And then the one big announcement for today's training is the HIP update. So Max sent out an email for all of this. So none of this should be new information, but if you guys haven't seen it, or if you have any questions, you want to clarify anything, I'll just go over the quick breakdown of everything right now. So the updates, we updated the C-frame from the old one to the current one you see in knee and nail. Then we updated the mallet similarly to the same one you see in knee and nail. And then we got rid of the giant femoral head puller and we put in the femoral head punch that you see in the anterior hip set. That should be a nice upgrade. I know nobody really seems to like that femoral head puller. And then the last one, it's an optional part, but we included the flathead driver. So that's for that screw that's on the hip extractor. If anybody wants a specific driver to be able to pull that thing out, now we have a driver for it. So just ask us, we can get you that driver. And then the next slide, here's a little more info.
And Mitch, I just wanted to add that the reason that we are doing this is one, obviously the mallet and the C-frame are better and we're getting rid of the giant space shuttle, but it's Stubra's effort to reduce strain on production, to reduce the number of parts we have to produce so that we get off back order and we have parts on the shelf. So this was primarily for that reason, so that we're not creating 3 different hammers, 3 different C-frames, and all these parts. We're trying to streamline so that we can produce enough to not only handle the demand, but all the growth.
Yeah, that's a good point. Yeah, these are now all the stuff for all the systems will be using the same similar components. There's no real reason why we can't do that. So now we're standardized, makes things a lot easier for planning, especially. Moving on with this, so cost, it changes a little bit, 22,500 up to 25,000. And then I'm sure you're all interested in this info. Quotes, for the current hip set, they ended at the end of the month, and any current existing quotes will expire on September 30th. There'll be a case-by-case basis after that, but the gist of it, they expire on the 30th. Shipping date, I talked to Anna and Adam about this. We'll start with availability by the end of the month, but that's when the first shipment of cases is expected. So roughly end of month is what we're looking at. Now moving forward, we'll go over the engineering side, materials today. So I'm not going to go super in depth. The goal is to just give you a brief overview of everything, give everyone a basic understanding on our material choices, some of the considerations we take into account that our parts go through when we're determining which materials we're going to use. And then towards the end, we'll also cover material sourcing, particularly from India. So I threw this slide in here just to give you all a brief overview of all the materials we use. At the moment, it's about 20 materials we use for our parts. Some of them obviously more common than others, but 20 total materials. It's a lot of things to order, a lot of things to work with. And obviously, this list is always expanding. So we're actually currently researching some new materials that might be added to this list in the future if all testing goes well and things seem promising. But at the moment, 20 different materials. All right, so slide number 1 and slide number 2 is also going to be kind of background stuff you guys might not know. The first 2 slides are stress strain curves. So these can give you a good understanding of basically what your part is going to act like. So I threw some definitions on here. Stress is just the force applied over an area. So it's basically a standardized force. So if you just think of it as a force, for all purposes, that's probably the simplest way to look at it. And then strain is going to be the change in length over the initial length of the part. Basically, just look at that as how much your part is, if you're pulling on it, at how much it gets longer, and if you're compressing it, how much it's going to shrink. And then the modulus of elasticity, you can actually see it on the graph here. If you plot your stress and your strain, that's going to be the slope of the line here. So stress over strain is modulus of elasticity. And then you can just see by plotting all the different points here, it gives you the shape. That shape, it'll change based on the materials, but overall, it's going to be a pretty similar profile overall. So you'll see on the coming slides kind of what I mean by that, but this is kind of the gist of what you're looking at. So going into a little bit of how the graph is actually made, if you put any material and you pull on each end, so put it in tension, you can also test in compression. Tension's usually more common. Most of the time, if we send stuff out, we're going to put it in tensile testing. You can see here, this is the typical profile they'll test, but really any shape works. We've made custom fixtures for some stuff that we've sent out for testing, so it might not be this exact shape. I know one I did was I threaded in a nail conical, and then we had a custom fixture so we could pull on the back of it where the C-frame would be pulling in an actual application. So you're not limited to this, but typically this is what you're looking at, which is what you see in this graphic here. So the graphic on the right shows basically what the material is going to look like in each portion of the graph. This again is going to remain the same no matter what the material is. Yeah, it'll change a little if it's brittle or ductile, but I'll go more into that on the next slide. But basically, you start with your standard material. As you pull on it, it gets a little longer. Once you get past this middle point here, it starts necking. So it starts to really thin out. And then you can see here, it's about to pull apart. And then at the end of the graph, that's where it actually pulls apart into two pieces. So that is considered the failure or fracture of the material. And basically, you plot all the points along the way, stress versus strain, and that gives you your graph. So now for a better explanation of how this actually affects our Shukla parts, by plotting stress and strain, you can get a good estimate of kind of how anything is going to act in the actual application that we need to use it for. So on the right, you can see a ductile fracture versus a brittle fracture. If you plot everything, you can see, so something like stainless steel is a lot more ductile than something like a ceramic, where it might be really strong up front. If you think about like a phone screen, it's going to be really strong, but as soon as you get past a certain point, it's just going to shatter. It's not going to end well. You're going to shoot glass, not into the patient because there's not going to be glass in there. But if we think about glass in the patient, it's going to shoot glass into the patient. And then on the left, this is just a comparison between a bunch of different materials. So you can see stainless steel, it's pretty strong, even compared to ceramic or glass. It's pretty strong. It's going to hold up to a lot, especially in comparison to plastic down here on the bottom. Different grades of stainless steel are going to be slightly different. They're going to vary a little, but the gist of it, you can see how ceramic compares to steels and bone and plastic. And that's kind of the gist of what I'm trying to show you here. The main reason I want to show you this is a lot of people will say, well, why don't you just use a super strong material like a ceramic, for example? Well, there's a trade-off, as you can kind of see here. A very strong material, they tend to be very brittle, so you don't need it to shatter if you go slightly past what you're expecting it to be going under force-wise. And obviously, every application, there's different requirements, so we kind of have to play around with everything, make sure whatever we're looking at, the requirements are going to work for the actual application. So some examples of that, if you think of like the conicals, if you need to actually thread into a part, conicals or screw extractors, if you're threading into a part, you need to cut threads into it physically. You not only need to be harder than that implant, but it needs to be pretty tough. So it's not just gonna, fall apart on you. And then another thing here is if you have two components that are rubbing together, I have a good example on the next slide. If you think of like a hip stem, you don't want two materials that are, you want to be in control of what's going to wear on the other one. So I'll just go right to that example so you can kind of see what I'm talking about. So material hardness, it's a measure of the resistance to localized plastic deformation. Basically what that means, the harder a material is, the less it's going to deform. And the Young's modulus, which we talked about, it gives you a pretty good estimate of what your hardness is going to be. But basically just think of a part that's resistant to scratches, dents, bending. That's a hard part, the more resistant it is. So if we look at this hip stem here, your stem itself, typically that's going to be, it's some form of metal, the titanium aluminum alloy, or maybe the old ones are stainless steel. And then the femoral head is always going to be harder, so cobalt chrome or a ceramic, and that's going to go either into a poly cup or a ceramic cup. The reason for that is you want the femoral head to not wear. You want that to be nice and smooth. You don't want any damage. You don't want scratches. You don't want dents. You don't want any type of deformation on that femoral head. So they're putting it into a softer material, which is why they'll go in and you'll replace the poly, but you don't have to replace the femoral head because there shouldn't be damage. Obviously, sometimes things happen and there's damage, but it's not from the two rubbing together. And then behind the liner, you're going to have a harder material again, so usually metal. And that's just so basically you're focusing all the wear onto the poly liner. Another thing you can look at is our carbide drill bits. So carbide is much harder than anything that you're going to see that's actually implanted in the body. The downside to the carbide drill bits is they look a lot like the ceramic on the graph here. They're very brittle. So if you aren't careful with them, they can actually shatter, and it's not going to end well. So it's just the trade-off. There's obviously a bunch of other considerations. The common ones, machinability, the weight of the material, the cost of the material, and then biocompatibility, obviously big in the medical field. If we were in construction or something, not really a concern, but since we're putting stuff in people's bodies, you got to look out for biocompatibility. I thought this chart was a good comparison. So we don't usually have to worry too much about conductivity or anything. This is a comparison between steel and aluminum, but machinability, aluminum is much softer, so it's a lot easier to machine. It's usually a bit lighter too. The problem is it's usually not strong enough, or it's going to deform very easily. So again, it just comes down to the trade-offs. You got to weigh all the options. And then there are some secondary processes that we can do to actually change these things. So surface coatings on the left here, usually these are applied just to add extra hardness on the surface or add some corrosion resistance so your parts aren't going to rust as easily. The hardness is the biggest one. We'll usually coat like the broken and stripped extractors just to give them that little extra bit of hardness so we can make sure they're going to cut into what they need to, stay nice and sharp and not wear down at the same time. And then on the right, we can also heat treat parts. So all of our steels, they're all heat treated. Basically what that does is you heat the material up, and it's gonna increase the hardness. It's again another little trade-off, so it'll make it a little bit more brittle. So if you look at this graph here, we can pretend this is your base material, and then as you get to different heat treats, so these are all different temperatures you get heat treat to, you can see you're getting harder, you're getting stronger, but you're also getting a little more brittle. It's going to fail earlier. This one in particular is looking a lot more brittle than the rest of them. So everything is a trade-off, I guess, is a good takeaway for this. And if you think of heat treating, it's actually, if you look at it like baking, you're basically playing around with the temperatures. You want to get the amount of time it's at that temperature correct. You want to get the actual temperature correct. And if you don't get it right, you can mess up the part. So there's a lot that goes into it, but we've been doing it for a while now. So quick breakdown on the common materials. We have stainless steel and then aluminum and plastics. So here's the full list of all our stainless steels. These make up the majority of our parts. Almost everything you see is some form of stainless steel. 17.4, obviously the most common. That's going to be in pretty much every extractor, every mallet head, that sort of thing. It's generally just strong, durable. It's very corrosion resistant. It's easy to get our hands on it. It's pretty nice to work with. It's our default material unless we have to change it for whatever reason. 300 series are generally a little softer, but they're also more corrosion resistant. That's going to be things like pins and springs that we're usually going to order from somewhere else. And then 400 series, these are kind of more the special applications. They can get much harder. They have a higher modulus of elasticity, which, if you remember, means it can basically withstand more force. Some of the issues are it can be tougher to source 400 series, but it's good for applications again like broken and strict extractors or the nail conicals, which they need to be harder. They need to be a little tougher, withstand some more. So we go with a little different grade of steel for that.
Mitch, why are the 400s harder to source?
They're just
doing it.
That's more of a planning would have a better answer than I would.
I was just wondering if it's global demand or if it's just not made as much as the other one.
I'm pretty sure it's more so like global demand. I know 17.4 is pretty common just for overall applications. 400 series, those are the ones that we'll typically have a lot of difficulty with, like shortages and things like that. Another downside to the 400 series is they're typically not that corrosion resistant. 455 is an exception because it's actually a pH steel, so it's similar to 17.4. But for the most part, 400 series, they're good for a lot of things, but then we have to start worrying about rusting issues. Aluminum, most of the time you're just going to be seeing it in our cases. We do have some other parts like the T-handle and the shoulder set. The actual handle that you'll grab onto is made out of aluminum. And there's a couple other parts. Some of the pros, it's real lightweight, it's cheap, easy to machine, very corrosion resistant. Those are all really good things, make it very nice to work with. The downside is it's soft, and the low modulus of elasticity means it deforms much easier. Kind of goes back to it being soft. And it's not super easy to use with steel. So a lot of times for strength purposes, we would need to kind of mix and match with aluminum. And that can give us difficulties, particularly if we need to weld parts. You can't really weld aluminum to steel, so that's a big downside. And then galling, again, goes back to softness. If you think of like the vice grip jaws, where you're inserting one jaw, that's one material, into the vice grip extractor, which the body of that is another material. The softer material of the two, so if we say that the vice grip jaw is made out of aluminum, it's not, but if we pretend it is, that jaw is just going to wear out super quick if we make it out of aluminum. Eventually, it's just going to start slipping out. It's not going to be a tight fit. It's not going to end well for anyone. So aluminum, we're pretty limited, but it is nice to work with when we can. And then the last thing here is the plastics we use. So there's a few different ones. Silicone, you probably all know, it's in our handles. It absorbs impact really well. And then acetal, That's what our mini handle is made out of, and also the bushings in the anterior hip extractor. So it's good for just kind of general larger plastic bodies like spacers, handle, that sort of things. And then Ultim and PTFE, they're real low friction, they're higher density, so they're stronger, but they're a little more brittle. They make good bearing surfaces because of the low friction and higher strength. So there's actually pieces inside the vice grip extractor and the maxi handles that you probably don't really even know are there, but they're in there just as bearing surfaces to lower the friction so you're not rubbing and wearing down, causing metal shavings. And then quick little story of what happens if something goes wrong. So originally the broken and stripped extractors, the materials were perfectly good. And then some testing was done and the decision to change from 455 to 440 stainless steel was made. In theory, this was a really good choice. It was harder than the 455, which would allow it to cut better. It worked good in initial testing. The unintended side effect was once these actually made it out to the field, some of them started shattering, mostly in off-axis applications, which weren't exactly tested in the lab. So sometimes things can happen because there's a lot that goes into materials, but you know, we do as much testing as we can, and we've got a good understanding of the materials. And then I'm sure you're all interested in this. So this is material sourcing in terms of how India gets their material, that when they make our parts. So long story short, we get the material and then we ship it to them. So we purchase it in the US, we ship it to India, then they machine it into our parts. India Customs inspects it. They have to check for waste material. It has to be under a certain percentage. Otherwise, they start to question why we have so much waste. So we machine things as efficiently as we can. It's basically the gist of that. And then after everything goes through customs, they're shipped back to the US, then they're quality inspected, secondary operations are completed, and then the finished parts are sent out for use. So again, the moral of the story, all of our material is sourced in the US, and then we ship it to India, they machine it, and it comes back to us. Right. And now this is a new section here. I'm just going to go over some of the common incident reports that we see, just so kind of everybody is aware of the issues we're seeing in the field and no one's caught off guard by anything. So mini handle is definitely the most common one. Some of you guys have probably ran into this issue. The two known issues we have is the driver will stop ratcheting or the driver will jam, won't be able to get a driver in or out. So the solution is actually, we're just fully redesigning it. It's essentially going to look the exact same. There's just another screw down at the bottom right here. Aside from that, looks the same, basically the exact same on the outside. The inside is what's changing. Currently, Austin has a prototype. It's ready for testing, so hopefully there's some updates on that soon. The next one, the tibial extractor, the modular jaw. If any of you have had this issue, this was a pretty common one a little bit ago. Now it's been resolved. So as you can see in the picture, the modular jaw was basically just exploding off. Not the best situation to be in. So we had to update the design. We tested it, and now these are actually in manufacturing. So like I said, shouldn't be an issue any longer, but just be aware if you have an older one, this is a potential issue. And then the last one I put on here is the maxi handle. So there's three known issues with this. It can stop ratcheting, the driver can jam, so just like the mini handle. And then recently we've also been having the epoxy start to come out on the bottom. We're investigating all three of these. I don't really have an answer for you guys on this one, unfortunately. We should have something pretty soon, but just so you're aware, if you see the epoxy coming out, you can swap it we'll get you a new one, or I think we can rework them. But just be aware of those. And then cases of the month here. So there's two. So Zach Shackelford and Chris Fishback. So Zach, he had a stuffy spine screw. So just some quick pictures of the case. He got it out successfully. And this is just a good one to call out for the deep well spine sockets. We actually specifically made these deep well spine sockets for the stuffy screws. So if you look at it, I guess the pictures, it's kind of tough to see, but they've got a deeper sitting hex that you need to grab, which isn't super easy. The current sockets are too shallow. They won't actually grab it. So now that we have the deep well sockets, makes that nice and easy. You just have your standard drivers. And these are special order, so you guys can order these if you just want to have them in the set. You can put them in the extra slots, or if you want to, just have some on hand. And the other one, Chris back, we'll watch this video real quick. All right. So if you don't know what was going on in that, they pulled out actually two tibial rush nails. So up here is a better picture. Looks like a little candy cane. They used the spine rod jaws out of the vise set. You can see down here. And surgeon really liked it. It was great. So I think this is the first one that I know of that uses the spine rod jaws in the vise set. So good job, Chris. And, another good sign for Vice. It's going to show up in a lot of different places. All your tough surgeries, hopefully Vice can help solve those. And then lastly, just reach out to the support email if you guys have any events or questions or anything. This lists some of the ideas what you guys might want to reach out for, but anything you want to get in contact with us for, feel free to reach out. And so thank you guys. That's all I got for today.
Great job, Mitch. Thanks
Hey,
for
Mitch.
everything.
Mitch,
Yeah.
hey, I got a question. So is there, for the new hip set, can they use the existing like extractors and a lot of the parts out of that and then just do an upgrade to it? Or is it gonna be, how can we work that?
Yeah, Kurt, we're working on an upgrade process right now. We're waiting for Suber to get back to talk to him from his dad's funeral. But the majority of the parts in there can be moved from one tray to the other. So we'll get back to you on that.
Okay, thanks.
Any other questions? I think we can all appreciate the boyfriend material slide.
Nice.
All right, if no one's got anything, I'll wrap up. You can always email the support email, support@Shukla Medical, if you have any questions that you come up with after the fact too. So, thanks everybody.